I'll let you take it away.
Oh. Yeah, thank you, John, and for the invitation. It's great to be here. Someday maybe I'll actually be there, but for now we do what we do, and so I'd like to talk about a geometric characterization of arithmeticity, and what I mean by that is in studying hyperbolic manifolds, there's this notion of arithmeticity and non-arithmeticity, and it's something that strikes fear in the hearts of many a geometer because it's not a geometric thing. It's an inherently geometric object that you have this notion that's not very Riemannian geometric. So I'd like to give just a brief tour of why you might care about these notions and some work that involves the following pair of teams. So it's originated in some work I ended up doing with David Fisher and John and Nick Miller, and there's a second set of work where John unfortunately became department chair, and so we took Uri Bader on board and proved some more theorems, but it's really saying something about what arithmeticity is geometrically. And it's a real pleasure to give this colloquium at OSU because, as we'll see as I tell the story, there's a great number of LSU people that really contributed to this story. So great. So to start, basically, the big problem is you want to classify closed Riemannian n-manifolds. Now, this is just way too hard, so we're going to start sort of whittling down the problem. And okay, well, maybe we'll start very softly. And so what's a closed one manifold? That's the circle. Okay, so at least I know the topological type, and now maybe I could talk about what metrics I would put on the circle, notions of distance, but that's not so bad. Hey, check. Okay, we'll call that one done. N equals 2. Now we have a classification of surfaces, and orientable ones, a surface of genus G with G handles, and then we have the non-orientable friends. And that's great. And so our first person of OSU fame comes in here because in studying geometric structures on these topological surfaces, very often what you use is a triangulation, and sort of famous theorem of Rado that you can triangulate these things. And if you take a course on, say, GX structures, using triangulations and cut and paste methods to build Riemannian metrics it's a real active area of research, going back to Klein and Ehresmann. Okay, maybe we need to study how to put some metrics on these, but it's a very classical problem. But for n equals 3, we start running into trouble already, in the sense that, at least in the first two cases, I could tell you all the topological types of, that we're going to make up my list of manifolds. For n equals 3, we don't have a list. We kind of do, and I'll get into this a little more later. But things become a little more difficult. And once you hit n equals 4, it's just over. So this is just far too broad of a problem. But over the last 50 years, there have been just a number of directions people have taken on this and honed down the problem. And so, one way to do it is to focus on important classes of metrics. And the one that's going to matter for me in this talk is a metric of constant curvature. And so what I mean there is that the universal cover of your space is going to be either the sphere, Euclidean space, so it's just Rn with its Euclidean metric, or hyperbolic space. So the classic spaces of constant curvature. And so then out of this, you get some discrete group of isometries preserving the metric, and so this group acts freely on either the sphere, Euclidean space, or hyperbolic space, and the quotient by that is m. So this is the classical setting of just constant curvature closed manifolds. And you can say, okay, well, I'm not going to classify all Riemannian metrics on all closed manifolds because I'm just not good enough. So let's just work on constant curvature. And what we'll see is that that's hard enough that we can do a lot. But I do want to mention briefly, I want to keep this talk not too technical and more of a story, but this setting actually fits into a slightly more broad setting of what's called a Riemannian symmetric space. And the reason I just want to bring this up is that this point of view actually informs how we study these cases, particularly the hyperbolic setting. So this broader setting of a Riemannian symmetric space actually really gives us a lot of the tools that we'll use to study hyperbolic manifolds. And so here what you have is that your universal cover, your model space for your geometry will be the quotient of some Lie group by a compact subgroup. It's the stabilizer of a point. So it's really just a sort of orbit stabilizer type statement where this K will be the stabilizer of a point in here, and I just identify the quotient. And then you have a discrete subgroup of this group G. And the point is that this K is compact. And so really I can just study this quotient G mod K. And the beauty of this point of view is that, I really want to study my manifold M. I can think about this as a sort of double quotient, but if you look at this G mod gamma instead, so this G is just the isometry group of this space, maybe the connected component or something. And now you can bring in tools from dynamics. So you're sort of expanding your toolkit to study these problems by using this more general point of view that goes back to Cartan. Cartan really cared about classifying these symmetric spaces and realized that the study of Lie groups was the way to bring in just a whole new group of powerful tools to study all of these. And so, and just to bring us back into this constant curvature setting, what I'll say is it ends up that the cases of hyperbolic space, so among all the things you can realize is these Riemannian symmetric spaces, the cases where I would argue we know the least about classifying closed Riemannian manifolds model on these symmetric spaces are hyperbolic space. And it has a complex twin that's the unit ball in complex n space with a particular Bergman metric. So this is the sort of complexification of this hyperbolic space. And I'm not really going to talk about this much. It'll maybe come back and poke its nose in the room at the end. But yeah, so like I said, among classifying these closed Riemannian symmetric spaces, really hyperbolic space is the one that has some of the most intriguing mysteries. But yeah, so back to constant curvature, let me just say a little bit about the sphere in Euclidean space, just as a warm-up, to sort of motivate why I think hyperbolic space, even in the constant curvature one, is the one where we have the most work to do. So if you think about the n-sphere with its nice round metric, then what do I want to get a quotient? Well, I want a free group, a group acting freely. So I want a subgroup of the orthogonal group, finite subgroup acting, and I want it to act freely so that my quotient is a manifold. So no fixed points. What does that mean? You just sort of put your linear algebra hat on, and that just means that 1 is not an eigenvalue of any non-trivial matrix. Okay? So now I want to go and classify manifolds with universal cover the sphere, and I'm really off and running. One thing is this classical theorem of Jordan, that you have an abelian subgroup of uniformly bounded index. So you could just start sort of rattling these groups off. If n is even, in fact, this can't have 1 as an eigenvalue. This is sort of just an exercise in differential topology. You only have the sphere and real projective space. That's it. Classification, done. Let's move on. Great. For odd n, you can do a little bit more. And this is an exercise. I'm teaching a course in geometric structures right now, and I gave this as an exercise to the students to work on. And for every odd n, find infinitely many distinct manifolds with universal cover of the sphere. And the ones you take are called lens spaces. I won't really define that, but it's just a natural cyclic group acting on the sphere. So, you can just, once I start boring you, you can think, okay, how do I get, Z mod 5Z to act on the 3 sphere? And little exercise if you haven't done it. But for n equals 3, you can just write down all the spherical manifolds. You've got the lens spaces. So you can classify those very precisely. You can sort of consider the 3-sphere and RP3 as lens spaces themselves if you want. And then, okay, now I just want to classify the finite subgroups of O4 that don't have 1 as an eigenvalue. And so you get some extensions of dihedral groups. These are called the prism manifolds. You get some extensions of the tetrahedral group, like the binary tetrahedral group, and there's an infinite family here as well. And then the binary octahedral and icosahedral groups. And there you go, whole list, done. And so, just to note, the famous Poincare homology sphere sort of fits into both of these families. It's the sort of intersection of the two. Okay, so you can just sort of implement this in any dimension. I don't know, what dimensions people have actually specifically written down. Here's the list of all spherical manifolds in this dimension. Well, I guess I did it in all even dimensions just a second ago, but like, have all the spherical 5 manifolds been classified? I don't quite know, but one can do it. And one can just, hand this to a computer or even a pretty good undergraduate and just say, go do it. And, whether they come back this semester, I don't know, either the computer or the undergraduate. But so it goes. Okay, so now how about Euclidean space? So let's classify the flat, the curvature 0 Riemannian manifolds. So now I want to look at discrete groups inside of, so now you just have Rn, it's just acting on itself by translation, and then the orthogonal group. And again, so this sort of becomes pretty classical. So Bieberbach proved that if you have a closed Euclidean manifold, then it's finally covered by the n-torus. And he was an unashamed Nazi, which is unfortunate, but this is a very nice theorem if you want to classify Riemannian metrics on manifolds that have curvature 0, because now what do? Well, I'm going to classify all the flat metrics on the torus. And just to maybe mention on the side, this actually comes back to this symmetric space point of view can be very helpful there as well. And then you can study finite groups acting by isometries on these flat tori, right? So I find these metrics and I study their isometry groups. And that fits into this picture of, well, my M is a quotient of a torus by some group acting by isometries. And so you can just go and do it. Not saying it's easy, but it's a plan. One might have to execute that plan. But so this has actually been done explicitly in low dimensions. So for n equals 2, you got the torus and the Klein bottle. You just sort of go to the classification of surfaces and you're done. For n equals 3, there are 10. So there are 10 Euclidean 3 manifolds, closed Euclidean 3 manifolds. So there's 6 of them are orientable and 4 of them are non-orientable. And this again goes way back, but again, Ohio State comes to the rescue in n equals 4. I learned this while preparing the talk. Zassenhaus was part of the original, this was maybe 78 or 79. This was written up and people have sort of streamlined the argument since, but there are 74 closed Euclidean 4 manifolds. 27 of them are orientable, 47 are non-orientable. And sorry, co-authors, you got dropped off, but okay, there you go. You all just care about the Ohio State names anyway. So great. But so again, there's like a program to classify Euclidean manifolds. Whether somebody's actually, gone and written it down is one thing. And I actually don't know if with the spherical case, I don't know if the case n equals 5 has been done for flat manifolds. Maybe somebody in the audience does, but I do not. But anyways, like I said, you can just go and do it. Okay, maybe we need to like classify the metrics on each of these and so on and so forth, but okay, fine. So, we're flying. We're only 15 minutes in and we're on our third out of the 3 geometries, right? We got constant curvature 1 out of the way, constant curvature 0. All right, well, let's kick this one out of the way. So hyperbolic n space. Now your isometry group gets a little bit more complicated. It's this almost simple Lie group. If you take orientation preserving, it becomes simple. So now it's you can identify the isometries of hyperbolic space with the projective isometries of this quadratic form. Okay, that just got a little bit more sinister than the previous examples, which was just the orthogonal group or semi-direct product of Rn with the orthogonal group. But you know, we go forwards with no fear, and at least in n equals 2, unfortunately we see our second Nazi of the talk, and I apologize. But for n equals 2, we know the surfaces at least. We have the list of the topological types. And so we can just go and we can study the metrics on them. This is very classical theory. You can think about this in terms of studying just discrete and faithful representations of the fundamental group into PGL2R. And so this is, again, very, very classical stuff. Goes back to Fricke and Klein. So that's great. So n equals 2. There's still lots of great open questions about this, but you know, in terms of, do we have a general good picture? Yes, we do. N equals 3, again, remember, we don't have a concrete enumeration of the topological types of 3 manifolds. Really, the problem in n equals 3, by the geometrization theorem of Thurston ... Perlman, the problem is the hyperbolic 3 manifolds. So the closed 3 manifolds admitting a constant curvature -1 metric, these are basically the thing that we don't understand well enough. So we don't have a concrete enumeration. We have a plan, though, that kind of fits into what I just described for flat manifolds. So every closed hyperbolic 3 manifold, so if your closed 3 manifold admits a hyperbolic metric, there's a finite sheeted covering space that's a fiber bundle of a surface over a circle. Okay, and this wins you a breakthrough prize. And so this is the virtual fiber theorem now. And okay, so this is kind of like saying that, you know, every flat 3 manifold is finitely covered by the 3 torus. And then I can think about studying just the 3 torus instead and looking at groups acting on the 3 torus. But, you know, things get a little hard. Okay, so now, you know, I don't want to just classify these bundles. I want to classify the finite groups acting on them. In fact, it suffices just to look at finite groups acting by what's called Mostow rigidity. You don't have to worry about them acting by isometries or not. If they act, then it actually will preserve the metric, which is fantastic. But also, you know, in terms of just enumerating these things, you know, there's really not a satisfactory enumeration of these bundles. You know, it really gets into just the theory of mapping class groups. And, you know, if I fix a topological type, I know which elements of the mapping class group I want, but I don't like have a good list of them. I can't just like enumerate them out and say, okay, here are the bundles, here are their properties, here are their automorphism groups, so that I can find all the hyperbolic 3 manifolds. And so this is very, very, very hard. But, you know, it at least theoretically fits into a similar picture as what you get in the flat case. So it's a matter, you know, here's a program that works in one case, and it's probably a little too hard to actually, you know, be a primitive recursive algorithm or something in this case. And now we move up one more dimension. So just to keep this talk going, I'm just going to go 4, 5, 6 all the way up and just keep going. But really what we see is that for hyperbolic manifolds of dimension at least 4, we're just clueless. We don't know anything. We know some things. We know a lot of things. We know how to build lots and lots and lots of examples. And we try to, Jean and I, in fact, try very hard to build lots and lots of new ones with new properties. And the point is, we have some tricks, and those tricks build examples, but there is just no sense in which we have any clue whether our tricks are even enumerating them all. We could be missing just large swaths of hyperbolic manifolds of dimension 4 and above. There could be ones that are just like dark matter to us as far as hyperbolic manifolds are concerned. We just can't see them, and we're trying though. We try, and so yeah. So this is sort of going to be the story of of the rest of this talk. And what do we know about the geometry of hyperbolic manifolds? What can we say? What can't we say? What can we build? And what would we like to build? Great. So what are some constructions? So I'm going to tell you about 3 constructions, and they basically up to variance are everything we know. All right. So the first thing is called the arithmetic construction. And this really just is generalizing the integers sitting inside the real numbers. The integers sit inside the rationals, sit inside the reals. And the integers act on the real numbers by translation with quotient the circle. Okay? And so that mentality is what the arithmetic construction is about. And the fact that the integers are really, a number theoretic object is what's going on here. So I'm going to go through each of these constructions we know with some pluses and minuses. From I'm gonna really keep my Riemannian geometer hat on. But yeah, so if you've seen this classical picture of SL2Z, 2x2 integer matrices of determinant 1 acting on the hyperbolic plane, that's sort of your second level. That's your second tier generalization of Z inside Q inside R. And then arithmetic groups are the broad generalization. Okay, so here's a plus. It works in all dimensions. Okay, so I can use this arithmetic construction to build you hyperbolic manifolds of any dimension you want. 101. I can build you a 101 dimensional hyperbolic manifold if you really, really want me to. I'm going to call this a plus and a minus, and I'll get into more as to why it's a plus and a minus. It exploits classical objects in algebra and number theory. So the construction uses number theory and algebra. And if you're a Riemannian geometer, you probably are not so keen on that. But it can also be a plus in that it can tell you geometric properties. And that's going to be where we're going. And so to build on that, and some more former Ohio State faculty come into this again. So this algebraic construction does allow you to find some geometric properties, things like volume. Volume gets related to things like the Riemann zeta function, which just sounds cool, right? Lengths of the closed geodesics in this metric. It's just fantastic. And really 2 of the pioneers of studying the geometric properties of arithmetic hyperbolic manifolds were Walter Neumann and Alan Reid, and Alan was a postdoc of Walter's at OSU. And in fact, that things that happened in your hallowed halls will come up later in this talk. And the big minus is that there are a lot of ways in which this is not geometrically hands-on. So for instance, I can build you hyperbolic 3 manifolds from this arithmetic construction. Now, okay, here it is. Agel tells you that I can find a finite cover that's a fiber bundle over the circle. I have no idea how to connect those two. I have this arithmetic construction. What can I say about this bundle structure? I have nothing. It's actually a really, I think, interesting problem to, there are these number theoretic invariants that you can attach to hyperbolic 3 manifolds. And then there are some other invariants that you can attach to this bundle structure, like it's dilatation or something as a pseudo anosoph. And like to connect those two, it's like, here's an algebraic integer. This has algebraic integers. Are they in any way connected to each other? I have no idea. And the last plus is that a computer can at least classify these. So there's finitely many of these of bounded volume, and it's a sort of consequence of the construction that you can go through and really classify them all. And it comes down to like classifying polynomials of bounded discriminant. It comes down to some really, it's hard, the devil's in the details. But you can go to a computer and say, give me all the hyperbolic 4 manifolds of volume bounded above by 15. And it can do it. And so that's great. if you want to actually like classify. And then this has actually been used to solve some important problems, this idea. Okay, next family, moving on. Reflection groups and Coxeter groups. So here's the sort of picture, classical picture, where I have a Z mod 2 acting on this torus, and now, okay, this was a nice flat manifold. Now this is a flat orbifold, and I have the group acting on the plane by reflections through sides of a square, right? So this is the, it's exploiting, really nice reflection groups and polyhedra, explicit polyhedra. And this is a real plus. This is a really explicit theory. You can actually, so I'm telling you, this is a new construction. Here's a new way to build hyperbolic manifolds. You can actually test, did it come from my previous construction up there? There's a way to just, sort of play around with invariance of these Coxeter groups and say, did this come from the previous construction? And Wimberg was the one that sort of pioneered this. And what he saw was that very often you can find examples here that didn't come from here. And so these are genuinely new things. And, he really was, I think, one of the people that pioneered finding interesting, concrete, non-arithmetic things. It's like, okay, here's this construction. Maybe I understand it, maybe I don't. But, give me other stuff. Give me new stuff, at least. And another plus is that this brings in some more OSU faculty, former and current, is that there's a strong connection between the algebraic properties of these reflection and Coxeter groups and the geometry. And lots of people have studied this. This is still a very, very active topic. And so I'll just leave it at that. But there's very powerful algebraic tools that give you geometric information. Big minus, though, is that, I can see Jean wants, 1,005 dimensional hyperbolic manifolds. And unfortunately, this construction can't give you one. And that's a real bummer. So it does have some strong limitations. And there's some other reasons why you might think this isn't giving you the like generic hyperbolic manifold. But it is a fantastic construction that's given us a lot of intuition into what hyperbolic manifolds should look like that we didn't get from the arithmetic construction. And, really, I would say the program that Agel implemented in order to prove this virtual fiber theorem for hyperbolic 3 manifolds was really strongly informed by these reflection group, Coxeter group methods, Artin groups, and so on. Okay, last construction out of 3. All good things come in 3s, constant curvature spaces and constructions of hyperbolic manifolds, except I'd really like a 4th one here. But anyway, so there's what's called the hybrid construction. So this has another plus in that it builds things for all dimensions, whereas the Coxeter and reflection groups couldn't. It's a sort of plus minus. It's very topological, modulo the arithmetic construction. So it bootstraps off of the arithmetic construction. So it's great because you're doing like cut and paste and you're really getting in there, but you're really getting in there with something that maybe you erase half your talk in excitement. Maybe you don't understand so well. So other geometric properties can be a little less clear in this construction. So let me give you a cartoon of what this looks like. So I start off by taking one of these mystery arithmetic manifolds and I cut it along a separating surface. So I have this mystery thing and I cut it in 2. Okay, so you bring out your hyperbolic cake knife and you slice off half the cake, and here it is. And it's got some boundary n. And it's what's called totally geodesic. I'll say what that means in a minute, but just think about this, in terms of just I have a space and I just cut it in 2. I just lopped it in half, right? And then I take another one. Okay, and there's some technical condition on it. Don't read this if you don't want to, that's fine. But I take another one. But the point is, I build these 2 so that they came from very different things out of this arithmetic construction, but this thing I cut along was the same for both, okay? And now I can just paste them together and I get a new space. And the theorem is what you get out of this is not from the arithmetic construction. These are all genuinely new. And so that's great. So now you know in all dimensions that at least the arithmetic construction isn't the only one. So yeah, this is due to Gromov, Piatetsky, Shapiro. There have been many variants of this exploited to different geometric ends in the ensuing years to build things with short systole and all sorts of things like that. But the point is, it's a really hands-on construction that gives you things that are not from this arithmetic construction. And so the remark, I'll just maybe say this quickly, is that this arithmetic construction, it's got some algebraic data. Unfortunately, you have to go and you go ask somebody that knows about, say, quadratic forms or something, and say, give me one that has these properties, and they say, okay, yeah, here you go. And the point is, modulo understanding a big bag full of definitions, this construction, finding, I need to define these spaces. I need to build them by hand. And it comes down to, at the end of the day, some linear algebra, some elementary number theory, and a whole lot of cleverness. But now the cleverness is considered pretty standard. So there's a little bit of sweat in the algebra hole that one needs to go through, but it's not so bad once you get through it a couple times. And so that's it. So I've given you a tour really of the three ways that we know to build hyperbolic manifolds. So in dimensions 2 and 3, we've got a lot more tricks. There's like Dane filling and all sorts of things. So in dimensions 2 and 3, we definitely have other tricks up our sleeves. But for dimensions 4 and above, this is all we got. And there's really no reason to think that this is everything. We could be just completely, like I said, missing the dark matter that makes up the mass of most hyperbolic manifolds. There's a sense in which we know that what we have is actually a lot of them, but I don't want to get into that too precisely. But so now I want to tell a story about what we don't understand. And this comes back to this question of, okay, there's this arithmetic construction where you have to go tug on a number theorist's sleeve and say, help. Can we turn that into something that's completely a Riemannian geometry condition? Okay. And so that's the story I'm going to finish with, is can I actually just say arithmetic things have this Riemannian geometric property, non-arithmetic things do not? That's the story that we're going to discuss. Okay. So I mentioned before, maybe I'll scroll back for a second, I cut my arithmetic thing along this half. So I cut it in half along something. I said this something was totally geodesic. What do I mean by that? What I mean is that I have a properly immersed submanifold, so that when I look at the map on universal covers, this is just an isometric embedding of hyperbolic spaces. Okay. Now, really, in general, you could really just take any embedding and then see what happens. And that's also totally geodesic. So I'm sort of, just to save myself some breath, including proper immersion in this. But so you have a properly immersed submanifold, and it locally is isometrically embedded. Great. Okay, so now a tour of what we know. If you're in even dimensions, every single known closed hyperbolic n-manifold contains a totally geodesic hypersurface. I'll just say, from a differential geometric point of view, there is no reason to believe this should be the case. So I think it's a very important open problem to find a hyperbolic 4-manifold without a totally geodesic hypersurface, because I think they're out there and we're just not seeing them, and we just don't know how to see them. And really, this is just an artifact of two things. The arithmetic construction always gives them to you. Reflection groups always give them to you. And the Gromov, Piatetsky, Shapiro construction always gives them to you. And so it's really the fact that, our known constructions just happen to always give you these hypersurfaces. If you're in odd dimension, you have to be a little careful. So you'll always have a properly immersed geodesic submanifold of codimension 1 or 2. So it might be a hypersurface, it might be codimension 2. And just to be honest, 3 and 7 are weird. 3 and 7 are weird because they're quaternions and octonions, and those give special arithmetic constructions, and those should scare you a little bit more, or maybe excite you. Maybe they excite you and we can talk, because it excites me actually, but okay, that's fine. So all known non-arithmetic examples have a hypersurface. And that's just an artifact of these constructions, like I said. There's no reason to believe that all non-arithmetic examples have a hypersurface. It's really just that our small brains can only build ones that do. And it's because our bag of tricks like exploits them in a really, really concrete way. So now here's something a little stronger. Oh, there's a theorem. Here's something a little stronger. In the arithmetic world, let's say I found one, okay? I found a codimension K geodesic submanifold. If I found one, then in fact there are infinitely many, and they're just everywhere. Now, I want to give you a little cartoon of that, just to give you some intuition as to why this might happen. So if I think about the n torus, this is just the integer lattice sitting inside of Rn. And inside there, the integer lattice sits inside the rationals. So what I can do is I can take a hyperplane that's a rational hyperplane. And that looks like this. There it is. And what that gives me is an immersion of a codimension 1 torus inside my quotient. But like rational hyperplanes, I pick any slope I want. They're just everywhere. And so that's really what's going on with this arithmetic construction, is that, once you find one, basically something of this nature of like Z sitting inside Q and Q being dense in R just tells you they're absolutely everywhere. And so these arithmetic things, once they have, let's say, one hypersurface, it's just a wash in them. Now, most of them they're just horribly immersed garbage, but they're just everywhere. And so with Jean and David Fisher and Nick Miller, we proved if you take one of these non-arithmetic things, it's built from this Gromov-Piateski-Shapiro construction, or some of the variants, not all the variants actually, but some of them, then there's actually finitely many. So an arithmetic hyperbolic four manifold has infinitely many distinct, properly immersed, totally geodesic hypersurfaces. A non-arithmetic one has only finitely many. Now, I'm going to scroll back up to the construction. So when you build this Gromov-Piateski-Shapiro thing, it definitely contains one. There it is. So out of this construction, you see this not arithmetic thing does contain one hypersurface. Great, there it is. There's only finitely many others. So there's sort of finitely many that are trapped over here. It's finitely many trapped over there. And that part was generally known, maybe not written down precisely before our result. But the point is, what we proved, the hard part was proving that you couldn't like have some chunk over here and some chunk over here. And you can only have finitely many chunks over here that glue to a chunk over here. That's really the point. So, OSU continues to be of critical importance in this theorem. And what we use is really something that comes from dynamics. And there's a long history of people that are associated with these so-called equidistribution problems. But really, it's the work of Shah that was, if you want to do closed hypersurfaces, if you want to do this closed case, it's really a beautiful little paper of Shah's that gives you what you want. But so the point is, if you have infinitely many, then they're everywhere. Okay, so just like in this case of rational subspaces of a vector space are absolutely everywhere, it's really like they are everywhere. And it's a similar thing here, where if you have infinitely many of these hypersurfaces, then they are as everywhere as you want. So you pick some, n-1 plane inside the the tangent plane, then there's one sort of passing right by that looks really close. Might not hit your chosen hyperplane on the nose, might not be tangent to that one on the nose, but it's pretty close. As close as you want.
Can I ask a question?
Yes, yeah, please.
So in your theorem, do you have a bound on the number of hypersurfaces that you could get?
No, and that's a fantastic question. Thank you for asking. I'm going to come back to that question later. Yeah, that is a fantastic question. I love it. So yeah. So I want to compare this to a really classical fact in Riemannian geometry, which just in negative curvature, if you have closed negatively curved manifolds, it's really classical that the geodesics are dense in the unit tangent bundle. Oh, maybe I should have, not tangent planes, I should have said frames, but okay, we'll just let that fly. Because I said so. So this is really, you don't expect this theorem. This is, I mean, I guess you do once you know the proof, but you know, this is just saying this is a very classical fact, goes back to Hopf and even before. So I'll only say a little bit about what we do, so our proof, we actually get into the guts. So, you know, there were these two arithmetic things that you cut into pieces and glued. And what we do is we get into the guts of this arithmetic construction and use a little bit of hyperbolic geometry to find non-absolute everywhere density, really. We find a little neighborhood of a point so that you don't see a geodesic hypersurface coming through there, and then we smash it with Shah's theorem. Okay, so that's the sort of brief sketch. But the point is, you know, I mentioned before, you can often connect this number theoretic nonsense that goes into the arithmetic construction to some concrete hyperbolic geometry. And the hard work in our paper is really a connection between those to find a little open set that then by Shah says you have to be finite. So that's the little sketch there. I'm going to skip this in the interest of time. Yeah, I'll skip that in the interest of time. But now the state of the art is if you have a hyperbolic n-manifold, n at least 4, then it's arithmetic if and only if it contains infinitely many what we call maximal totally geodesic submanifolds. So I said before, if you're arithmetic, once you have one, then they're everywhere. Right? We prove that's an if and only if. So this is a completely geometric characterization of arithmeticity. And so what does this maximal mean? Maximal just means it's not contained in something of bigger dimension. And that's a genuine worry. I'm not going to get into why that's a genuine worry, but it is. And the other point is that if n is even, then hypersurfaces suffice. So let's just, you know, try to parse this theorem in the case of hyperbolic 4 manifolds. So there's this mysterious arithmetic construction of hyperbolic 4 manifolds. So I'm going to, as a differential geometer, I'm going to hand you a hyperbolic 4 manifold. And I'm going to ask you, is it arithmetic? What you'll do is you say, well, does it have infinitely many distinct, again, I'm erasing my talk. Does it have infinitely many distinct, totally geodesic hypersurfaces? If yes, arithmetic. If no, non-arithmetic. And so, you know, arithmeticity has now been reduced to a completely differential geometric condition about just properly immersed submanifolds. It's also true for hyperbolic 3 manifolds. This is, you know, maybe even to me the most interesting case. You have to be a little careful because there's a way, this is sort of related to the existence of the quaternions. There are arithmetic constructions that just have no surfaces at all. Okay, so you have to be a little careful. So if I have a hyperbolic 3 manifold that contains one totally geodesic surface, just one, then it's arithmetic if and only if it has infinitely many. Okay, so you have to have the first one. You can have arithmetic and non-arithmetic things that just have none, and you're just toast. And okay, so there's the case of hyperbolic 3 manifolds with just no totally geodesic hypersurfaces. Those could be arithmetic, they could be not. Can't do anything about it. Once you have one, then you have infinitely many, if and only if you're arithmetic. And I should say the compact case here was also proved by Margulis and Mohammadi by different but similar methods. So it's also a super rigidity theorem of sorts, but it's a sort of similar strategy, but the guts of the proof are very different. And I'll just say that this was a question of Allen's and of Kurt McMullen. So I guess when I was a grad student, Allen started poking about this for hyperbolic n-manifolds for all n, and Kurt had thought about the three-dimensional case. But I want to give you a really concrete application to knots in the three-sphere. Okay, and so this is a combination of work of this previous theorem with work that Allen did while he was an OSU postdoc. I confirmed with him this morning. He actually proved this theorem in the halls of Ohio State University. So if you have a knot in the three-sphere, so that the knot complement admits a complete hyperbolic structure, finite volume, then it contains infinitely many immersed, totally geodesic surfaces, if and only if it is that knot right there, the figure 8 knot. And the point is, this is just our previous theorem, plus Allen proved that this is the only one that gives you an arithmetic hyperbolic three-manifold. But so to come back to the previous question about counting, okay, so let's take another knot complement. Can I say anything about the number of totally geodesic surfaces, right? So pick a knot in the three-sphere so that it has hyperbolic complement. It has finitely many totally geodesic surfaces. I can give you an example with none, the knot 820, okay. But let's say it's got one. Does it have others? How many can it have? And this is where I get to sell my own graduate students' work. This is thrilling. I think this is just fantastic. So my students, Conley and Rebecca Palmer, who will be on the job market next year, prove that if you take the twist knot with M half twists, so there's just M here. Yeah, brown is good. Okay, so M equals 2 is the figure 8. So if M is at least 3, then this knot complement is hyperbolic. It's known. And since it's not the figure 8 knot, it has finitely many properly immersed, totally geodesic surfaces. And what Con and Rebecca proved is that there's exactly one. And there it is right there. If you look at this, this is a thrice punctured disk. So you've got the sort of meridianal, follow the meridian, then you've got punctures there. So that thrice punctured disk, that's totally geodesic. And it is the only one. That's it. It's the only one you get. That's fantastic. So yeah, is there anything else I wanted to say there? And so using some like classical covering space theory methods, actually what they proved, and this all, I mean, Allen was also thinking about this geodesic surface while he was at OSU, and it's just fantastic, but sort of unpublished question of his whether this was the only one. But then using some like classical covering space of knot theory tricks, they actually proved that for every k greater than or equal to 0, there are infinitely many commensurability classes of hyperbolic three manifolds with exactly k. So what are you going to do? You're going to find, covers of these knot complements. So this has exactly k lifts. And so the k equals 0 case was known before, but sort of beautiful bootstrap on these knot complements. Oh, I gotta be a little careful. It's true for all m, but there's a prime condition. I don't want to lie about their theorem, but yeah. Anyways, so I think maybe just to close, I think there's still lots of great questions, and they're really centered on this. I mean, challenges for the future: build hyperbolic four manifolds, with no totally geodesic hypersurfaces. Build closed hyperbolic three manifolds with exactly k totally geodesic surfaces for every k. There's just a lot of great classification questions, and so I think this really sort of pushes at where our knowledge is of how to construct hyperbolic manifolds, and these geodesic hypersurfaces play such an important role in our constructions. I think there's great work that's been done and lots of great work to be done. So I will finish there. So thank you for your attention.
Thank you very much, Matthew. So I guess we can open up the floor for questions. Anyone would like to ask a question? I don't know, do people put questions in chat or do people just jump in and talk? What's the easiest protocol here? Well, let me ask. So in the Coxeter example of Coxeter hyperbolic manifolds, we know that they're virtually fibered. Is there an estimate in terms of the combinatorics for the degree of the covering which fibers over the circle? I mean, this is sort of asking the counterpoint of the arithmetic setting, where you said that it's not so easy to see what degree fibers. Is it any easier in the Coxeter setting? I don't know. Maybe Mike's got a quick answer to that.
You're talking about three manifolds, right?
Yeah, three manifolds. Yeah. Yeah, I don't know.
Actually, I will say there's a paper by Kasia Jaskiewicz, Norin and Wise, where they virtually fiber Coxeter groups. And so that's an algebraic virtually fibering, but in the world of three manifolds, what they do is by Stalling's theorem producing a fibration. So you might be able to make that effective.
Effective, right? Okay.
Maybe.
I'm talking right now. All right.
That would be my best. Theirs, I think, only works with
good.
certain Coxeter groups, but still, I think that's an interesting angle.
Starting point. Okay.
I think this is Mike Davis again. I think when they said virtually fibering, they were just talking about whether the kernel of the map was finitely generated. The kernel of the map to Z, they had a map to Z with finitely generated kernel. They didn't mean it actually, they never had any actual fibrings.
Right, but by a theorem of Stallings for three manifolds, that's equivalent.
For three manifolds, it's the same.
Yeah.
Yeah.
But I think they probably never fiber in higher dimensions.
No. I think you're right. I think, I think it's an interesting question to say geometrically what that kernel is. But
I mean, there's nothing like pseudo-Anassov,
No.
because the mapping class group of the hyperbolic manifolds finite group or something instead of.
Yeah, that's right. Yeah, it can't be it can be a sort of maybe like a broken fiber bundle or something. Something like a Lefschetz fibration, maybe, where it maybe looks nice most places, but there's some bad places. Yeah, no, it in fact can't be a proper fiber bundle. I think even you can use Morse theory to prove that these kernels can't be finitely presented. I think in higher dimensions, they're finitely generated, but they can't be finitely presented. I forgot why that was.
Other questions from the audience? Well,
It was a good talk.
Thank you.
Yeah. All right. Well, thanks, Matthew. Maybe. Yeah. Thanks for giving us a great talk, and yeah, we'll touch base on that stuff at some point.
Yeah, we'll get back to it eventually.
Yeah. Thanks a lot. It was very enjoyable.